Hello! In this video, we will look at PID control. PID control is a control method that keeps the actual output from a process as close to the target or set point as possible. It consists of a combination of proportional control, integral control, and derivative control, and can be widely applied to process control such as speed, flow, pressure, and temperature. For example, it can be applied to maintain a constant flow rate and pressure by setting target values such as flow rate, pressure, and water level as shown on the screen, and compensating for deviations or error by comparing them with feedback from sensors. Now, let's take a closer look at the concept of PID control. First, let's look at the proportional gain. Proportional gain is the gain used to output the manipulated variable proportional to the deviation or error between the target value and the feedback value. The larger the set value, the smaller the deviation. But if it is too large, the control state becomes unstable. Next, let's look at the integral gain. The integral gain outputs the manipulated variable by integrating the deviation. Since the deviation is not completely eliminated by proportional control alone, integral factor is used to eliminate the steady state offset. In the inverter, when the accumulated error is 100%, you can set the time until 100% is the output. For example, if the integral time is set to 1 second, when the error is 100%, 100% is the output after 1 second. If the integral time is too short, overshoot or vibration will occur. If overshoot occurs as shown on the screen, decrease proportional gain and increase the integral time. Then the overshoot disappears. If a long period of vibration occurs, increasing the integral time stabilizes the vibration. Finally, let's look at the derivative gain. The derivative gain is produced by multiplying the slope for the deviation by a time constant and adding the result to the PID input. PI control can control close to the actual target value, but there is a disadvantage that the response performance deteriorates when the disturbance is large, so derivative gain is used to compensate for this. When the derivative time is set to 1 millisecond, if the error change rate per second is 100%, 1% is output every 10 milliseconds. If the derivative time is lengthened, the manipulated amount increases and the responsiveness increases, but overshoot or vibration may occur due to overcompensation. Conversely, if shortened, overshoot due to overcompensation can be suppressed, but the amount of operation may be small and the responsiveness may deteriorate. As shown on the screen, if a short period of vibration occurs, setting the derivative time short will reduce the vibration. If shortening the derivative time does not reduce the vibration, reduce the proportional gain, or increase the PID output low-pass filter time constant. Now, let's see how to program parameters related to PID control. First, go to APP1 of PAR mode and set application function selection to process PID2. Then, parameters related to PID control will be displayed. When PID-related parameters appear, the first parameters to be set are APP20 PID reference source and APP21 PID feedback source. The PID reference source means how to set the target value or set point, and the PID feedback source means how to receive the detection value or feedback. If APP20 is set as a keypad, the target value can be entered into the APP19 PID reference setting. The currently set target value can be checked in APP17. The next is the proportional, integral, differential gain, and forward compensation gain. The proportional gain is set in percentage, but note that the integral and derivative gains are set in units of time. The forward compensation gain, expressed as F gain, is a gain that can be added directly to the PID output by setting it as a ratio to the target value, so you can get fast response characteristics. PID output value and feedback value amount can be checked in APP16 and 18 parameters, respectively. So please adjust the gain value while checking these two parameters. Next, we will learn a little more through application examples. Let's say you have a system that pumps water from the left tank to the right tank, as in the pump system you can see on the screen. The purpose of PID control in this system is to maintain a constant water level. The water level is continuously measured with a water level sensor, and the feedback value is fed back to the inverter. Now, let's program the parameters using the keypad. First, press the mode key once to move the PAR mode, and then move to the APP group using the right arrow key. Then, use the down arrow key to move to the APP number 1 parameter and set the value to number 2 process PID. Then, PID-related parameters appear and allow to be programmed. Then, go to APP19 and set the target value. In this example, we will set it to 50%. In APP20, you can select the target value setting method. In this example, we will set it as a keypad. In APP21, you can select the PID feedback source. In this example, we will set APP21 to V1 to arbitrarily change the feedback value by adjusting the input voltage with the volume resistance. Let's set the proportional control gain of APP22 to 30% and the integral time of APP23 to 50 seconds, and the PID output scale of APP32 to 100%. After all parameters are programmed, let's run the pump and check the operation. If the feedback value is smaller than the target value at the initial startup, the frequency of the inverter rises quickly. The rising or acceleration speed depends on the proportional gain, integral time, and derivative time settings. If the rising speed is slow, increase the proportional gain and decrease the integration time. In the case of loads with low variability, such as pumps, the differential gain may become unstable, so please be careful when programming it. However, if the proportional gain is set too high or the integration time is set too short, the feedback value of the sensor also rises rapidly, and the control amount exceeds the target value as shown. In this case, the control amount becomes negative, and the inverter decelerates. After that, when the feedback value reaches the target value of 50%, the manipulated variable decreases, and the inverter's operating frequency stabilizes without significant fluctuations. Next, let's look at the pre-PID function that can operate at a constant speed without PID control, only when the feedback value is low at the beginning of a startup. Pre-PID function is a function that performs normal acceleration without PID operation up to the set frequency when an operation command is entered, and starts PID operation when the feedback value increases to a certain level. When the difference between the target value and the feedback value is very large, it is difficult to expect a rapid increase in the feedback value with only the compensation amount by the PID gain. Because of this, using the pre-PID function can quickly increase the feedback value. PID control starts when the feedback value reaches the preset PID start level. For example, since the pipe is not filled with water at first, it takes time for water to start to immerse in the right water tank. So the state with a large deviation between the PID target value and the PID feedback value may be maintained for a long time. In this case, since the compensation speed may be faster to operate at a constant frequency than to compensate for deviation through PID control, you can use the pre-PID function to operate at high speed when the feedback value is small. Next, let's look at how to set pre-PID. If general acceleration is required without PID control operation, enter the target frequency for general acceleration into APP34. For example, if APP34 pre-PID frequency is set to 50 Hz, normal operation continues at 50 Hz until the control amount is greater than the size set in APP35. However, if the feedback value does not reach the level set in APP35 during the time set in APP36, a pre-PID fail trip occurs. Please be careful not to set the time in APP36 too short or set too high. Now, let's use the keypad to set the parameters related to pre-PID. First, press the mode key on the initial screen to move to PAR mode, and then press the right arrow key to move to the APP mode. Then, move to APP Group 34 and set the pre-PID operation frequency. In this example, we will set it to 30 Hz. In APP35, set the level to start PID operation. In this example, we will set it to 30%. In APP36, set the delay time until the PID operation starts when the feedback value reaches the level set in APP35. In this example, we will set it to 10 seconds. After all parameters are programmed, let's run the pump and check the operation. Let's look at the functional behavior in the pump system. Previously, the operation frequency of the APP34 PID controller was set to 10 seconds. The operation level of the APP35 PID controller was set to 30%, and the operation delay time of the APP36 PID controller was set to 10 seconds. If the PID feedback value is less than 30%, it will operate at 30 Hz for up to 10 seconds. If the PID feedback value reaches 30% or more within 10 seconds, the constant speed operation stops and PID control operation starts. When the PID feedback value approaches the PID target value, the frequency becomes stable. If the PID feedback value is less than 30% and the state is maintained for 10 seconds, a pre-PID fail trip is generated and the output is cut off. Next, we will look at a sleep and wake-up operation, which can save energy by saving energy when the feedback value remains high enough during PID control. Sleep and wake-up is a function that stops the operation completely when the feedback value rises above the target value and the state that no further operation is necessary continues for a certain period of time. This function automatically restarts when the feedback value decreases below the set level. For example, as in the pump system that can be seen on the screen, when the right water tank is full and there is no need to operate the pump anymore, it is driven at a very low speed by the PID control. At this time, the inverter can cut off the output to save energy and enter a power-saving state. This is called sleep in relation to sleeping. If the water level in the right water tank goes down, the inverter cancels the power-saving state by the wake-up function and restarts it. This is called wake-up. Now, let's look at how to program parameters related to sleep and wake-up. If the inverter's operating frequency is below the frequency set in APP38 sleep frequency and continues to operate for the time set in APP37 PID sleep DT, the operation stops and enters the PID operation sleep mode. In APP39 and 40, the standard for starting PID operation in PID operation standby mode, sleep, is set. If 0 below level is selected in APP40, PID operation restarts when the feedback value is less than the value set in APP39 PID wake-up level. Number 1 above level starts operation when it is higher than the value set in APP39. Number 2 beyond level restarts operation when the difference between the target value and the feedback value is more than the value set in APP39. For example, if APP39 is set to 35% and APP40 is set to below level, when the feedback value falls below 35%, it wakes up and restarts. Now, let's use the keypad to set sleep and wake-up related parameters. Press the mode key on the initial screen to move to PAR mode, and then press the right arrow key to move to the APP group. Then, move to APP group 37 and set the PID sleep mode delay time for the operation to enter sleep mode. In this example, we will set it to 10 seconds. In APP38, set the PID sleep mode frequency for entering sleep mode. In this example, we will set it to 20 Hz. In APP39, set the feedback value level, which is the criterion for wake-up. In this example, we will set it to 25%. In APP40, set whether to start PID operation above the standard or below the wake-up level set in APP39. In this example, we will set the level below the wake-up level so that PID operation can be started. After all programming is done, let's run the pump and check the operation. If the water level in the right water tank exceeds the target water level, the operating frequency is reduced by PID control. If the operation is performed for 10 seconds at a speed of 20 Hz or less as previously set in the parameter, the operation is stopped and the PID operation enters sleep mode. In the sleep state, if the water level in the right water tank decreases due to some reason, and the PID feedback value is less than 25%, the inverter restarts. Thank you.